This is a lesson on Pascal's triangle and some of its applications. Pascal's triangle is a pattern. You start at 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. You have a series of rows, series of terms going after that. If I want to get the next row of this triangle, I take the two terms directly above it and add together. So I'm going to have a 1 on the outsides, and then it'll be 1 plus 3, which is 4, 3 plus 3, which is 6, 3 plus 1, which is 4. So 1, 4, 6, 4, 1. That's the fourth row. If I want to do the fifth row, 1, and then I add 5, add 10. I'm adding the terms on top of it. 10, 5, 1. Then again it'll be 1, 6, 15, 20, adding 15, 5, 1. That's a pattern for Pascal's triangle. Should note that it starts at 0. This is actually row 0, term 0. This would be row 2, term 0, and this would be row 2, term 2. Okay, so it starts at zeros. You can tell what row it is by kind of the diagonal right here, kind of tells you what row number it is. So it starts at 0, then goes row 1, row 2, row 3, row 4, row 5, row 6. Pascal's triangle is symmetrical in that 1, 6, 15, 20, and then it repeats itself. 15, 6, 1. Or 1, 5, 10, 10, 5, 1. It repeats itself. It is symmetrical. First couple of questions we're going to have is, for example, what term? Term row 4, term 3 came from what two previous ones? So row 4, term 0, 1, 2, 3 came from these two previous ones, which were, it was term row 3, term 2, plus term row 3, term 3. You added those two up, you got the term row 4, term 3. If I was to add up from row 7 to 6 plus term 7, 7, that would give me on the 8th row, and if I was to add them up, it would actually give me the 7th term. It's the term number from the second term in the equation you're adding. So if I had term, let's say 9, 5 plus term 9, 6. If I was to add them up, it would give me my 10th row, and it would actually give me my 6th term on that. Okay? That's the first type of question you'll see with Pascal's triangle. The next feature we're going to look at is just an interesting property of Pascal's triangle. 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. Interesting property is if I was to add up the terms in the row, so let's say I add up this row, I'm going to get 1, add up this row, I get 2, add this one up, I'm going to get 4, add this one up, I'm going to get 8. You do the next row, 1, 4, 6, 4, 1, I'm going to get 16. Notice how the sum is doubling every time? It's actually a power of 2. This is 2 to the exponent 0, 2 to the exponent 1, 2 to the exponent 2, 2 to the exponent 3, 2 to the exponent 4. It's the 4th row, and it's 2 to the exponent 4. The 5th row would be 2 to the exponent 5. So the sum of the nth row is actually 2 to the exponent n. So if you know what row number it is 2 to that exponent will give you what that entire row adds up to. So if I want to find the sum of the 5th row, it'll be actually 2 to the exponent 5, which is 32. You can find out what that entire row adds up to. Okay? Just an interesting property. It will come into play with future probability questions. The next thing I can do is I can expand binomials now using Pascal's triangle. So if I have 3x plus 5 to the exponent of 4. If I use the 4th row of Pascal's triangle, which is 1, 4, 6, 4, 1. And I follow the pattern. I have my first term and I have my second term. My first terms start at high exponents. So we'll start the exponent of 4 and then that kind of counts down. 3, 3x to the exponent 2, 3x to the exponent 1, and 3x to the exponent of 0. It goes from 4, 3, 2, 1 all the way down to 0. The second term starts at a 0 and counts up. Counts up till you get to a 4. Now, and I just put some plus signs in between, and you've got your answer. Now you can expand it a little bit further, you can do a little bit of algebra to try and simplify it, but that's just the basic pattern of doing that binomial expansion. Take the next one, where it is 2x minus 1 to the exponent of 3. Take the third row of Pascal's triangle, 1, 3, 3, 1. Take your first term, 2 to the x. Start it high. Start at exponent of 3. Counts down. All the way down to 0. Take your second term, the minus 1. Start at, bracket, minus 1. Start it at 0. Have it count up. Put your plus signs in between. You got your binomial expansion. First term starts high, goes down. Second term starts low at 0 and counts up. And you have your coefficients, which are the row of Pascal's triangle. Okay, that is the second application. Then you get some counting applications with Pascal's triangle. So let's take a road map. You're standing here, this is you, and you want to get to your house over here. How many different ways are possible if you're just going to go in the general direction here without any backtracking? So I want to follow, if I go down this road here, there's only one way to get down to this location right here. Now that's just me walking straight down this road. Same as if I decide to walk across this way here. There's really only one way I can get to this location. I'm just going to walk straight across that road. But if I was to get to this location right here, I can go this way or I can go this way. There are two ways for me to get to that location. If I want to get to this location right here, I would have had to come from either this spot, which is one way to get to that spot, or from this spot, which there's two ways to get to that spot. So that means there's three ways in total. The one way from here and the two ways from that location. And as you can see, this is starting to build on Pascal's triangle, where my new number comes from the addition of the two previous ones. So if I wanted to get to this location right here, well, I would have had to come across from that way, which there's two ways to get to that one, or I must have dropped down from that spot. Total of three different ways. And as you can see, Pascal's triangle start to build, so I can just continue the pattern. 1 and 3 gives me a 4, 3 and 3 gives me a 6, 3 and 1 gives me 4, and then I would have 5, add it up, 10, 10, 5. Now you might get to a location where there's no road that goes down. So there's no way I can drop that 10 down to this spot. There's no road that does that. So to get over here, well, I'll have to figure it out. Same as this road doesn't come down here, so there's no connecting, so my 10 would just come straight across. I'd have a 15 here from adding up those two. This 10 and this 5 would add together to get this location here. And this 10, 15 would add up to give me 25 on that spot, and then I would have a total of 40 different ways to get to my destination. Using a different example, same thing, trying to get to a certain location here. There's a house right here, but I can't go through this spot. So I start putting ones across, ones down. Now these two cannot add up. I can't get to that location, so I have to bypass it. So my 1's going to drop down here. This 1 would come across because there's no number that can come from that one. And I can start adding up here because both roads are applicable, both roads are applicable, both roads are applicable. And then you'd have just 8 locations. You can start to play around with what intersection to block off would cause what to happen. Okay, so that's the number of ways to get from one destination to another destination using Pascal's triangle. So let's say you're playing a game of checkers. You want to get from one end of the board to the other end of the board. Here's your checkers right here. You can only, it's on the white blocks. You can only drop onto the other white blocks. But you have a roadblock here. For some reason, you don't want to go onto that spot. How many ways to get to the top of the checkers board? So you start saying, well, if I move this direction, there's one way to get there, one way to get there, one way to get there, and so far across. One way to go in either direction to get to a certain location. If I wanted to end up in that block right there, well, I've had to come from this one, or I would have had to come from that one. So there are two ways to get to that. Using Pascal's triangle of adding the two previous ones up. So doing that, 1 and 2 gives me a 3, 2 and a 1 gives me 3. Follow the same pattern. 1 and 3 gives me 4 here, 3 and a 3 give me a 6. I start adding up. This is a roadblock. I cannot jump into that location. Can't happen. So there's no way, there's no carry forward number to use. So I'm going to have just a 1 in that location here. I'm just going to have a 6 in that location. And you start to continue to fill it out. 14, 16, you'd have 7 right there. 8, you'd have 23, you'd have 30, and you just have a 14 in that location. So if you're playing checkers, you know in this scenario, the most likely outcome is for them to finish in that spot right there. If they have that location blocked and they have that location, there's where they're starting from. How many total ways can you get there? Well, you would add it up and you'd have, let's see, 31, you'd have 61, you'd have 75 total ways to get up to the top of the board. Okay, and the last example for Pascal's triangle is the number of ways to spell a word if it's set up in kind of like a picture diagram like this. And you need to find, you want to spell Pascal. Okay, so you need to have all these letters. Well, start using Pascal's triangles formula to actually figure it out. To get to that S, I could have came from the A, either A. There's two ways to get there. And you kind of add up the previous two numbers to get to the new one. "20 ways to get to use all the letters P-A-S-C-A-L-S in different versions to get to spell the word Pascal. You could have went down here, across, down, across. I would spell Pascal. Or you could have did another version of how to get to all those letters. Okay, so there's 20 in total. These are some of the applications of Pascal's triangle, counting methods. Okay, you can use your expansion of a binomial using the pattern, and then you have the cool property of the sum of the whatever row is 2 to the exponent of n, and then actually figuring out what the term is using the little term formulas. This is a short lesson on Pascal's triangle. Thank you very much.